Hey everybody, today we're going to go ahead and look at the structure of acids and bases. This video lesson is going to talk about why an acid behaves the way an acid does, and it's going to give us the reasons why bases are very good at pulling hydrogen ions. And it really all comes down to atomic structure. So if we understand the atomic structure of the elements or the particular compounds we're talking about, we can go ahead and explain why we see those various properties. Okay, so let's go ahead and start with the first part, which is to look at the factors that affect acid and base properties. So what we're looking at are two things. We're looking at the bond polarity. So we're looking at how polar the bond is. How we're talking about the positive and the negativity of it. Okay, so we're looking at hydrogen and fluoride. We're looking at the partial negative and the partial positive. That's what we talk about when we are talking about the bond polarity. Okay, when we're talking about the bond strength, we're talking about how strong the two atoms are held together. So there's a strength to this bond that's holding those two atoms together, and it's based on the diameter of the two ions that are together, in this case the two atoms. The closer they can come together, the stronger the bond. So we need to keep in mind that the polarity and the strength are two different things, and students kind of get this mixed up all the time. They think that if a bond is really, really polar, then it has to be really, really weak or really strong, whichever, but it's not the case at all. So if we want this hydrogen ion to pop off, we want two things to happen. So in order for an acid to be the best acid it could possibly be, we want this hydrogen ion to easily be removed. So two things we want. We want the bond polarity to be very high and the bond strength to be very weak, so that this positive charge attracts other negative charges, and when it attracts it and they stick together, this bond easily breaks. So those are the two conditions that we want to have for very strong acids. So when we look at those strong acids, things like hydrochloric acid, nitric acid, those conditions are set up so that those hydrogen ions are easily pulled off. High polarities, low strengths, okay? So that's really the goal that we're looking at as we go through. So let's start with our binary acids. This would be things like HCl, HBr, things like H2S, so two atoms in our system. In order for these acids to be strong, the stronger the acids, again, like I said, high polarity, weak bond energies. Okay, so we're looking for elements that, or acids that have that scenario. So if we take a look at our periodic table, what we're going to do is we're going to look at chlorine and bromine and sulfur, because we're talking about binary acids. We're looking at a binary or a monatomic anion. A monatomic anion meaning a chlorine, chloride, or a bromide, just a single element in that acid. So if we look at the first thing, remember, there's two properties, bond polarities and bond strength. So if we look at the polarities, now this is going across the period. Okay, so if you look in your periodic tables, it's going from left to right across the periodic table. So we got carbon, nitrogen, oxygen, and fluorine. Well, if you look at the bond energies, there's really not much going on with the bond energies. They're pretty close together. They're all in that 400 to 500 range. So there's not much difference. There's no trend, I guess is what I'm looking for. There's no trend in the data when we go from carbon to fluorine across the periodic table. But something else changes as we go from carbon to nitrogen to oxygen to fluorine, and that is that the electronegativity goes up dramatically as we go down this column. So as I go down the column, the electronegativity is getting stronger and stronger. So that means right here we're going to have a very strong negative and a very strong positive, because a very high electronegativity difference. Again, we get a little bit weaker, gets a little bit weaker, and then it gets so weak that we really don't have much. The electronegativity between carbon and hydrogen is almost exactly the same. So as we get to fluorine, the electronegativity goes up. So our acidic properties, from going from left to right on the periodic table, increases because of the high electronegativities. So we have here is an acid, hydrofluoric acid, not a strong acid, it's still a weak acid, but still an acid nonetheless. Water is neutral, this is a base. So here we have an acid, something that's neutral, and something that's base. And then over here, neutral. Okay, this isn't even going to have any sort of properties at all. This is neutral because it's in the middle. It can either be a base or it can be an acid. This is neutral because it's not going to not because it can form either one. It's not going to be, it's not amphoteric is what I'm getting at. And then down here we have a strong acid, Then we've got another acid. This is a weak acid. Now we're getting back to that basic property, and then again we're going to have something that's really not basic or neutral. It's going to end up being neutral. So we can see that on the right side of the periodic table, due to the high electronegativity, we're going to have a more acidic substance. Okay, so that's the game we're playing. We're looking at the atomic structure of the nonmetals, or the anions in this case, and how they relate to the hydrogen ion. Okay. All right, now I'm sure you can imagine what's going to happen as I go down the family, as I go down a family on the periodic table. We're going to see that the bond strengths are going to dominate. So here we can see that the bond energies get smaller, 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 and smaller as I go down in the periodic table. So now I'm looking at fluorine, I'm looking at the halogens. So we're looking at our halogens here, which would be the fluorine, chlorine, bromine, and iodine. So as I go down, the electronegativity actually gets lower and lower and lower. But what happens is the acid strength goes up. Okay, acid strength actually goes up as I go down on that periodic table. Okay, so the reason for that is because the bond strengths are lower. Okay, so here it's going to be a little bit different. Even though this is the most electronegative, and this is really, really positive, whoops, take that back, is really negative, and this side's really positive, yeah, well, it's going to be a good case, you know, it's going to be attracting, it's going to make it acidic, but because the bond strength is so strong for the fluorine and the hydrogen, that's what makes it a weak acid. It's the high bond energy of the hydrogen and the fluorine, the fact that they're really small ions or atoms that come together to create the bond and create a relatively strong one. So then hydrochloric actually becomes our strong acid. So these are the strong acids. Well, this is still considered a weak acid. Okay, and the reason for that has to do with with the bond energies between those atoms, because you're getting a bigger and bigger atom. So as I go down, the atomic radius is small for fluorine, gets bigger, gets bigger, gets bigger. And since the atomic radius gets bigger, the bond energy gets weaker, and therefore we get a stronger acid as a result. So hydrofluoric is most polar, but the strong bonds override that. Okay. All right. So as you go down the periodic table, you get a more acidic acid. And as you go across on the right, you get a more acidic acid. So you might want to write that on your periodic table. You can write down the periodic trend and the group trend. So going from left to right or from right to left, it's up to you. But the acidic properties tend to be follow that trend. The right side of the table, the halogens and the nonmetals, tend to form our acids, while the other side of the periodic table, the alkali metals, make the bases. Okay, and we'll talk about that in just a second. And that's why they're called alkaline, because the word alkaline refers to base, acidic or acid refers to acid. So alkaline, alkalinity, acidity, acids. Okay, so let's take a look at oxyacids. So when we talk about an oxyacid, we're talking about an acid that had oxygen in it. Now this sodium hydroxide, you should know that. Now this, I'm kind of playing around with the formula a little bit. You guys are used to seeing this written like this. This would be your hypochlorous acid, HClO. We tend to write it like this because you guys have memorized ClO as hypochlorous, or actually the hypochlorite ion, but we put it in the acid, it's hypochlorous acid. Okay. The reason I'm writing it this way is because this is not the way the bond looks. This is not the way it is. In reality, what happens is the hydrogen is bonded to oxygen and bonded to chlorine. Same thing over here. We're going to have the sodium is bonded to the oxygen and bonded to the hydrogen. Whenever you have oxyacids, whenever you have these oxygens that are going to be acidic with a hydrogen ion, it's always the hydrogen ion bonded to the oxygen, not to the nonmetals. So bond strength is really the same. So here we're looking at bond strength being the same because it's both a hydrogen-oxygen bond. So when we have a oxyacid, it's that OH that makes it acidic, and it's that hydrogen here. Now in this case it's going to be a base. We're going to see why, because it has to do with the fact that I have that sodium ion in here, okay, versus the chlorine ion. Alright, so acidic hydrogen ions bound to the oxygen. Okay, so consider why. So again, considering this, I'm going to put in a metal. Alright, so the metals have a very weak electronegativity. If electronegativity is very low for the nonmetal, it means it's not really attracting electrons. What's happening is electrons are being pulled in this direction, being pulled in this direction. What you end up with is a net result of the electrons staying on the OH, and therefore you get sodium hydroxide. sodium hydroxide. You get that base properties. Why? Because the sodium, the metal, is not very good at pulling the electrons. So therefore what it does is it creates that sodium positive, which pops off, and that OH minus, which obviously also breaks off, and you get your basic substance, or your basic solution. So the reason why this is a base is because of the fact that the sodium ion is very bad at pulling electrons. Now if we compare that to the chlorine one, if I substitute in chlorine with oxygen and hydrogen, well now chlorine's even better at pulling electrons than oxygen, so therefore electrons are moving in this direction, they're moving in this direction, so we end up with is a buildup of electrons on this side, and the hydrogen ion is standing alone on its own with a positive charge. So what we end up with is ClO minus and a hydrogen ion. This is different because now we have that chlorine in here with the higher electronegativity. Since it has a higher electronegativity, it's pulling the electrons more in this direction, creating that break here, and we get the acidic solution. Okay, so why is it that this forms an acid? Is because of the electronegativity of the nonmetal. So when you have a nonmetal with OH, with the hydroxide group, you get an acid when you put a metal in here, and this is again what I'm saying. Things like sodium ions or sodiums, lithiums, magnesiums, and bariums, these are all alkaline because they make alkaline substances. They make basic substances. Chlorines, bromines, fluorines are going to make acidic substances. Okay, so let's wrap it up. Okay, the last little bit that we're going to talk about is when we compare these nonmetal ones, because we've got these series of acids. Take a look. We got HClO, HBrO, and HIO, right? We've got hypochlorous, hypobromous, and hydroiodous acids. Now, if we're looking at these, they're all going to follow the same pattern. So whenever you have oxygen in here, it's hydrogen bonded to the oxygen, bonded to this. Hydrogen bonded to the oxygen, bonded to bromine this time, and then of course HI, okay, with the O in the middle. Again, the bond strength is the same, so we can't say anything about bond strength when we deal with the oxyacids. So therefore it has to do with the electronegativities. Since chlorine has a higher electronegativity than the iodine, we're going to expect the hypochlorous to be a stronger acid. And notice that the Ka is smaller, or a lot bigger than the Ka for the hypoiodous acid. Okay. Again, why? Because of the electronegativity differences. So if I just substitute in an element that's more electronegative, it makes that polarity greater than the polarity down here. Okay. All right. And then the last thing to look at is when we look at the series of same elements. So now I've got, well, let's draw it down here. No, actually, that's not bad. Okay, so I got chlorine, and I've got the hydrogen. That would be the first one. That would be the hypochlorous. Now to look at what goes on here. I've got the chlorine bonded to an oxygen, bonded to a hydrogen, bonded to another oxygen. That's the formula, or the Lewis structure, for the chlorous acid. Okay, and again, what happens here is the fact that I'm adding more electronegative element. Notice electronegativity here is got 2 elements. Here the electronegativity has 3. It's going to make this more polarized, making this more positive, making this easier to remove, therefore making a stronger and stronger acid. So the more oxygens I put in here, the greater, okay, the greater the increase in, let's try that again. The more oxygens I put in here, the greater the increase in electronegativities, therefore the higher polarization of the bond, and therefore the stronger the acid. So it all depends on what that anion is that you're working with when you're dealing with acids. Okay? Alright, so that would be your rundown on your structure of acids and bases, and I guarantee you're going to see something like that on the tests, on the AP test, on my test. You really need to know how to be able to explain these properties using electronegativities and bond strengths. Alright guys, I'll see you later. Thanks.